Hi, everyone. We are here to talk a little bit about the, the speed, flow, and density relationship. What does that look like using the fundamental equations that we've talked about in the past? This is the Q equal to SD, which is the fundamental relationship of uninterrupted flow. Remember, this relationship only applies when you're talking about a flow where there are no traffic signals, where there are no stop signs on the main line and the traffic is flowing. So this is, for example, your I-5 freeway or on the main line and the US 101 in most places where there are no traffic interruptions within within the main line. So this Q equal to SD basically gets derived from this here. The flow rate is equal to space mean speed times the density. And then you could have other relationships. For example, this is another independent equation. S is equal to A minus B and D. And I talked to you about how speed and density are variables in this relationship, while A and B are constant parameters of this relationship that can be derived based on the slope and intercept. So this equation, this linear relationship, so these are blue dots are the real data points, and then this is the fitted line here that I'm drawing, a loosely fitted line, the best fit line. And when speed and density have a linear relationship, we call that equation Greenshields model of speed density relationship. And then this Greenshields model can then be used to derive the speed flow relationship and flow density relationship, where whenever the flow becomes maximum, that's your capacity point. Now, the best thing to do this would be to understand this with the help of an example. And let's say if this is what we are given here, that S is equal to 55 minus 0.45 D, which is the Greenshield model. And now we're trying to figure out, based on this Greenshields model, could you estimate flow density relationship? Could you estimate speed flow relationship and the jam density and the capacity of the roadway segment? So there is a roadway segment where we are saying that the speed and density relationship looks like this right here. So this is my speed density relationship. And again, it's a Greenshields model because the speed and density are linearly related. There are other types of models, as I mentioned in the other video. Those models are Greenberg's model. We discuss a little bit more of in-depth discussion of these speed density relationships in our CE 529 modeling and simulation class. But for now, Greenshields model, which represents the linear relationship between speed and density, would be sufficient for our purposes. So your job is to find the flow density and the speed flow relationship. And what I want to do here is I want to take this example problem and see what we can do with this. So basically what we are given in this example is the equation of this line right here. We're given this equation, the equation of this line is given to us as 55 minus 0.45 D. So your speed is equal to 55 minus 0.45 D. Now, if this is the equation of this line, that's what's given to us. And you can see that it has a negative slope here because D is the x-axis variable and the coefficient of x is the slope of a line. I hope you know that from your Algebra 1 discussion. And then the other thing you can derive from this is that when density equal to 0, when density is 0, so that's your y-intercept. So when you're talking about this point right here, when you're talking about this point, density is 0 at this point because it's a point on y-axis. But what happens when density is 0? So if you substitute density to be 0, D equal to 0, you end up with S is equal to 55 miles an hour. So that means my speed value is 55 miles per hour at this point. What does that mean? That means this is what I call my free flow speed. the speed at density equal to 0. So my free flow speed is speed at density equal to 0. Okay. Now, could I also derive the other parameter of this relationship, or the other thing about this relationship is, could I derive this value here, which is what I call the jam density. We talked about that last time. If I want to derive the jam density, is density of the roadway, how many vehicles per mile, when speed becomes 0. So there is so congested that nobody can move. That's my speed equal to 0 point. Density will be pretty high at this point. To derive that, I can do that. What I can do is I can take the speed. I can take my equation of speed equal to 55 minus 0.45 times d, and then set speed equal to 0. So I set speed equal to 0. So if I cut that out and just say speed is 0 now. Okay, when my speed is 0, I can solve for d, which will be 55 divided by 0.45. And that value comes to be, if I use my calculator here, so my density turned out to be 122.22 vehicles per mile when I solved this. Now I need to derive, in the example problem, first thing they asked me was flow density relationship. If I want to get flow density relationship, I need to get the flow in the picture. Right now I have speed density, but I also know that I have an equation that can help me derive the relationship between all three variables, Q equal to S times D. So all I need to do is Q is the flow rate equal to speed times density. And I want flow and I want density. So I want this Q in the mix. So I want the flow in the mix. Yes. Right. So I'm going to say, okay, I want the Q and I want the density. I don't want the speed. Okay. So this is my flow, speed, and density relationship. In this relationship, I don't want the speed. I only want flow and density. So I want flow and density. I need to just substitute speed with something with density. But remember, I have that directly here. I have my full relationship. S is equal to 55 minus 0.45 D. That relates speed and density. So all I need to do to find flow density is just replace Q equal to, so take the S times D. So take the S and replace that by 55 minus 0.45 times D. And there you go. I can simplify it a little bit more. I could say Q equal to 55D minus 0.45 times D squared. Right? So I could write it like that. I could say 55 times D. And this becomes a sort of a quadratic equation. If you look carefully, it's a quadratic equation in flow and density. Q and D are my variables here. Now, if you look at slide number 14 here, which I hope I can enhance a little bit. You look at slide number 14, and if I could go back to my annotations. I'll take out some of these annotations from last time. If I'm looking at this chart right here, this equation actually represents this chart, where D is on the x-axis, Q is on the y-axis, and this is 55D minus 0.45 D squared. Now, I've already told you that capacity is the maximum flow rate. That's represented by this peak of this parabola. And I hope you can think about ways to derive what that peak would look like. How can I find the peak of this parabolic relationship? That will give me the capacity. Okay, it's a quadratic equation. So all I need to do then is find out dq over dd. So if I take the differential of this equation, so find the maximum of a quadratic function is basically you take the derivative of the function with respect to the x variable. and you set that derivative equal to 0. Okay, so that's when your y variable is maximized. When maximum flow rate is there, dq or dd should be 0, and dq or dd in this equation would be equal to, so if I take the differential of this equation right here, it's 55d. The differential of that would be 55 minus 0.9 d times d. So this is just a simple derivative with respect to d. And then I could say, okay, I set that equal to 0 to find my maximum flow rate. And then if I set that equal to 0, it's pretty easy to then solve the value for d. And then d will come out to be 61.11 VPM. So if you solve 55 divided by 0.9, you'll get 61.11 vehicles per mile. Now, remember, this is not capacity. This is not capacity. Remember what this is. You have to be kind of thinking about this, that this value is actually right here. This is 61.11 in this example. So this is the value that I've found. This is not capacity. This is just a density with respect to capacity. Right? Now, if I want to find capacity, that's pretty simple. I can just plug into my equation and just plug in the value 61.11. So if I want to find what I call Q max or capacity, is obtained by plugging in equal to 55 minus 55 times 61.11 minus 0.45 times 61.11 whole square. Okay? So I hope you can all see that, how I'm getting to that value. This is what gives me the Q max or the capacity value, 51 times 61.11 minus 0.5 by 6.11 whole squared. And that's pretty easy to solve. I'll let you do the arithmetic here using your calculators. And that's the capacity value. If you were to actually do the arithmetic, you'll get about 1680.55 vehicles per hour. So remember the units here. The flow rate will be always in vehicles per hour. Density will be vehicles per mile. So always remember the units. So I want to make sure that you are considering the units here. So this is vehicles per mile. This is vehicles per hour for the flow rate. And then for speed, obviously, it's miles per hour. So always I'll be looking for these units in your answers when I ask you for capacity. And remember, 61.11 vehicles per mile is not capacity. That's the density corresponding to capacity. Is not capacity. It's density corresponding to capacity. And so if you want to find the capacity, you need to go back and find the Q max by plugging in that density value. Now, the next thing I wanted to do is ask you for speed flow relationship. Okay, ask you for speed flow relationship. So let's go back to this chart here. So I'm going to go back to this this chart right here. So taking off some of these things. Okay, so speed flow relationship is also pretty easy. Now we got the flow density calculation right here on your left, but I want to do the speed flow modeling on the right. Again, this speed flow chart is actually pretty important because that's the chart that we use for level of service estimation as well. But let's first kind of work on our speed flow relationship, how we can derive that first. And the way you derive it is is again make use of the flow equal to speed density. This is a fundamental relationship. What I want to derive now is speed flow relationship. Okay, I want to derive speed flow relationship. So I can go back to my relationship of Q equal to speed time density. So I can go back to that fundamental relationship of uninterrupted flow. And I could take Q is flow rate. So if I want to stamp it, I want speed flow, right? So I want the speed. Oh, sorry. I want the speed. So I want this. So I want the speed. I want the flow. And I don't want density. Okay, I don't want density. So if I want only these two, all I need to do is replace the density in this relationship from this equation. So if I take this, my D, so if I want to rewrite that relationship of Q equal to 55 minus 0.45 D, I can write that in the form of D equal to 55 minus S times 1 over, or divide that by 0.45. Okay, so take 55 minus S, so just kind of manipulation of that, and I get my speed density relationship written in the form so that I can eliminate density from the speed flow density model. Okay, so I want speed, I want flow, I want speed, I don't want density. So all I need to do then is say Q equal to S times density, which is 55 minus S divided by this whole thing divided by 0.45. Okay? Now, the good thing about this relationship is that you could actually do what you did here on your left. What you did with respect to density, you can still do it with respect to speed to derive capacity, because then you'll be deriving the peak of this relationship right here. Okay, so you could differentiate this, because remember, Q is now on the y-axis, so I should probably erase this. Q is now on the y-axis, and if you're trying to find capacity, if you're trying to find the capacity is right here. Okay? Capacity is right here. So if you're trying to find that capacity, you can take this relationship, differentiate it with respect to S, okay, dq over ds, set that equal to 0. Then you can find here speed corresponding to capacity. So this point here is speed at capacity. So this right here is speed at capacity. Okay, this value would be speed at capacity. I can derive that. And then I can find the corresponding value of flow rate by substituting the speed at capacity into it. And then I'll get my maximum flow rate like that. And maximum flow rate, by the way, will come out to be the same exact value that you got from the speed flow density relationship. So they should come out the same. So that's something that you should practice and check and see if you can repeat the process that you see on your left on your right as well. So that'll be a great practice for you. So now what we have done is we've solved all the problems that this example problem asks us to solve for. So we've gotten the flow density, the speed flow density, the jam density, and the capacity all have been found. And now you've solved your problem. Thank you so much.